Hello everyone. In our previous lecture we have seen different kind of state machines and how to design those patterns using state machines, how to detect patterns using state machines. Now one problem which we have observed in during one of the examples, that what if we design a state machine which has redundant states. So to avoid a redundant states, one method could be that we design it very systematically. We think of all the combinations, and then the solution, whatever we come up with, is already a minimized and the optimized one. Now, is there a possibility that if we come up with a method, if we come up with the states which are unoptimized, and can we optimize them later? So then the first question also comes in our mind, that why do we would like to optimize, or why we would like to reduce the number of states? So reduction in states is directly related to implementation. So if you see that if more number of states are there, more number of flip-flops are required to store that state, and also if more number of states are there, the next state logic depends on the previous state. If the number of states are more, then the logic will also be more, so that means more gates would be required. And if more gates are required, then of course more area would be required, and further there is a good possibility that it would also have an impact on latency and delays. So it is always a good idea that if we can reduce, if we can optimize or minimize the number of states, then it's always good. But how to do that? So if we want to reduce the number of states, then we have to say that some states are definitely, there are some states which are actually equivalent to some of the existing states. How do we know that two states are same, or actually could be represented using one state? So one idea could be that if a particular state, given any input, the two states will have the same transitions and same outputs. So let's say if they have same transitions, they have same output, so that means those two states are equivalent, and which also means that one of them is redundant. So let's try to understand this particular statement with one of the example which we had done yesterday. So yesterday in our previous lecture we had done one of the sequence detector with which was taking 4 disjoint bits as the input. So basically group of 4 which were non overlapping as well as disjoint, and the pattern which we were detecting were 1001 and 1010. So if the pattern is 1001, then the output is 1, or the pattern is 1010, then the output is 1. And incidentally, the way we have derived it was an optimal state machine, and it was already reduced. So let's say if we try to create in a naive method where we are not having any optimization, but we are trying to create all the states, all the possible states. So then this state table would look something like this. So I'll briefly explain this state table. So you remember that initially we'll start with the reset state. So a reset state, let's say, is A. So if present state is A and input was 0, then we'll come to B state, and if input is 1, then in next state is going to be C. Output is always going to be 0. Now in case of B, we are assuming that input sequence 0 has already arrived, and so the present state is B. Now if the next input is 0, then the state is D, and if next input is 1, then the state is E. Similarly for state number C, this is actually C. So this is C. So from C, I'll correct it. So if the current state is C, then the next state, if next input is 0, current input is 0, then it will become F, and otherwise if input is 1, then it will become G. So in case of state number D, the input pattern 0, 0 has already arrived, and in case of E, 0, 1 pattern has already arrived. So in case of F, 1 0 has already arrived, and in case of G, 1 1 has already arrived. And now from the D, let's say if input is 0, then we can have H state, and if input is 1, then I state. Similarly, J, K, L, M, N, and P. So all these possible states are there. So what is the significance of significance of H state? H state means 0 0 0 has already arrived. Now if next is 0, then we are going to reset state, and if 1, then also we are going to reset state, but the output in both cases is going to be 0. So similarly for I state, 0 0 1 has already arrived. Now if another 0 will come, we have to go to A state, and similarly if next is input is 1, then also we have to go to A state, but the output is going to be 0. So output 1 would be there in case of 0 1 0 1. So basically if the previous information is 0 1 0 and the current x equal to 1, then the output is going to be 1. So similarly the other output which is going to be 1 is 1 0 0 1. So when the present sequence or the past sequence is 1 0 0 and the next the current value is 1, then the output is going to be 1. In all other cases, so this represent all the 16 scenarios. So in all other cases, all the 8 scenarios, so in all the 8 scenarios the output is going to be 0, so it's going to be 1 only in these 2 cases. So this represent an exhaustive state machine, which means that we have written each and every possible state which could be possible. So if we can optimize this, then possibly the same method we can use to reduce any number of state. Now let's see how do we reduce. So let's remove this input sequence part, which was showing the significance of each and every state. So then this table would look like something like this. So now if we see this table, then try to see that what is the difference between state number P and state number N. So in N state, if input is 0, then the next state is A. If input is 1, then also next state is A. And output in both cases, input 0 as well as input 1 is 0. So similarly for the P, if the input is 0, then the next state is A, and if input is 1, then also next state is A, and output for both the cases is 0. So that means P and N should be actually the same state. We don't see any difference between these two rows. Similarly, if we see that there is no difference between P, N, M, and K, and I, and H, all of these rows, they are all same. So if they are same, then we can possibly say that all of them are same. So wherever I, K, M, N, P, all of them are written, we can replace them with probably H, and we can remove these rows because they are all redundant. So for removing, I am putting cross, so all of these rows would be removed. Now similarly we see that J and L, these two are also looking same because their next state is same and their outputs are also same. So I can remove that. So now I can either choose J or L. So I incidentally choose L, not J. So we can do the other way also. Now the next step would be that wherever J is there, I have to replace it with L, and wherever I, K, M, N, and P is there, I have to replace them with H. So so that means wherever I found I, K, M, and N, I would replace them with H. And similarly, if J is there, I'll replace it with L. So now if I look at further, then it appears like this. These two rows, E and F, these two rows are also same. Now E's next state is L when input is 0, and when input is 1, the next state is H. output in both cases is 0. Similarly for F also, if input is 0, then next state is L, and when input is 1, next state is H. So that means these two rows are actually same. If they are same, so that means we can remove one of them. Okay, and similarly if you see so we can remove, let's say, F1. Now let us say the other thing is also there. If you see D and G, for D the next state is H if input is 0, and if input is 1, then also it is H. Output in both cases is 0. Similarly for G also, the next state is H in both the cases if the input is 0 or input is 1, and output for both the cases is 0. So that means we can remove one of them. Let's say we remove G. So wherever G was there, wherever F was there, now we have to replace them with E. So we have replaced them with E also, and now so with this we can find what is the final table. The final table looks something like this, which has only A, B, C, so only 7 states are there: A, B, C, D, E, D, E, F is not there, D, E, H, L. So these are the only states. So that means we can reduce. So what is the learning from this whole exercise? That what we have done, we see if 2 rows in my state table is same, that means those 2 states are same. So can we apply, and the second thing which we have learned, that we can apply this particular information, this particular knowledge recursively till there is no further equivalent state found, or there is no further removal of state, there is no further rows which are same could be found. So this looks like a simplistic method, and we can find equivalent states and we can reduce our state machines, and doesn't take too much of time also. So let's try to apply that on some other example. So this is the another example. Now let us try that can we reduce any of the states. So if we see here, these 2 rows are different. Even if you spend couple of more time, you can pause the video for some time and then look at these rows carefully. You will not be able to find any opportunity. So can we still say that this is an optimized state machine? So when we have such a state machine where there is no obvious reason to merge, or obvious reason to say that these 2 states are same, then what should we do? So then we the method is little sophisticated, but let's try to understand what are we trying to say. We are saying that these 2 states, A and B, these 2 states could be same only and only if D and F are same, C and H are same, because outputs are same. Outputs are same. If these 2 next states are same, then we can say these A and B are also same. Okay, so we can apply this kind of a fundamental relation, and then see the possibility that when 2 states could be equivalent. So if we are able to resolve, and then we can if 2 states are not same, then we can remove that particular relationship and say that because these 2 states are not same, so they are actually not same. So then because of that, some other relationship may also be will also be false, and which would keep on distinguishing that if 2 states are same or not. Whatever is left would mean that these 2 things are same. So let's try to understand what I am saying. So I understand that it's slightly tricky to put it in words. So let's see with the example. Now I'm putting this table in a corner of my slide so that we can create this kind of an implication method or a pair based method. So in this pair based method, what we are saying is for each pair, for each, let's say the pair A and B, we are trying to see when they could be equivalent. So in this pair method, we try to have all possibilities. So for example, for A and B, A is here, B is here. So we see that A and B could be equivalent only if D and F are equivalent and C and H are equivalent. If any of them is not equivalent, that means A and B is not equivalent. Now similarly, we try to put all the possibilities, all the pairs, and see that whether they could be equivalent or not. Because A is equivalent to B if B is also equivalent to A, so that means that this particular matrix will become lower triangular matrix. There need not to A to A. Basically, this particular cell is not there where we are comparing A to A, because A is actually equivalent to A. So similarly, the upper half of the this matrix is also not there. Now let's quickly look at all the cells of this matrix. You see A and C. If we see A and C, we don't care whether the next states are same or not, but because outputs are different, so A and C is bound to be different. So that's why we already put across here that A and C are not same. Now similarly, we can see for A and D. For A and D, they could be same if A and D are same and C and E are same. Now this condition, if A and D are same and this additional condition A and D are same, so we can remove this condition. They would be equivalent if C and E are same. So let's again look at A and E. So if we see A and E, then because their outputs are different, so they are not going to be equivalent. So similarly, we can see A and F also have different outputs, so they can never be same. Similarly, A and G could be same if D and B are same and C and H are same. So we have created all the pairs, and for every two states, whatever pairs are possible, we are writing it here. So let's look at the one which are little exceptional rules. So for example, CE, you see. So if you see CE, C and E could be same if E and C are same. So that means this particular relation E and C is also redundant. We can remove that. And C and E are same if A and D are same. Okay. Now let's look at G and B also. So if we say G and B, F and F are already same. So G and B would be same. G and B would be same. G and A, sorry, G and A, G, what we're looking, G and B. So G and B would be same if F and B are same, because H is already there, which is same. So that's why B and F is written over here. The second term is not written because that is already found to be same. So this way we are, yes, of course it is little painstakingly processed, but because it's a tabular method, we can do it using computers. We can simply put things into computer. We can say that whether in first loop we can find out all the dependencies or all the pairs, which if those pairs are same, that means for example D and E are both found to be same, then that means and C and H are both are the same, that means A and B could be same. And reverse is also true. If any of them is not same, that means there is no possibility that A and B could be same. Okay, so now let's look at the second possibility and try to see. So I have removed this table so that we can focus on this matrix, and I have also removed A and D because this pair is, this particular cell is for comparing A and D, and similarly I removed C and E also. So now in the first iteration, so first we have created this lower triangular matrix where for each comparison we have found that what could be the equivalence requirement. So if these I'm again repeating, if these two are same, then only these two pairs are equivalent, then only this A and B could be equivalent. Reverse is also true. So let us see if A and B are equivalent or not. So let us see at D and F. D, we have to see here F and D, because D and F is not same, so that means A and B can never be equivalent, so we put a cross here. So that means A and B cannot be same. So now let's look at C and E. C and E, this is E, this is C, so it depends on A and D, we don't know. So now let's look at A, F, E, H. For A and F, is also, this is A, this is F, so this particular cell is corresponding to AF, which means that A and F are not same. Because A and F are not same, so that also means that D and B cannot be same, so we put a cross here. So this we have already seen. Now let's look at E, F, B, D. So whether E and F, for E we look at F, we don't know about E and F. Can we say anything about B and D? For B and D, yes, B and D are not same, that we have identified, so we have to mark this also as a cross. But let's do that in the second iteration. So in first iteration we try to see all the possibilities which is there from the original list. So C, F, A, B. AB also we have identified that it's not equivalent, so that means we can cross this also, but let's do that in the next iteration. Now let's look at B, D and C, H. B and D, yes, B and D is also crossed, so that means this G and A will also be crossed. So now look at B and F, B and F, yeah. So B and F is not equivalent, so that means this particular cell is also not going to be equivalent. Now look at A and B. So this will this is because of A and B, will cross this in the next iteration. Now let's look at C and E. So C and E, C and E depends on A and D, we don't know, but D and G, D and G, we don't know about D and G also. A and G, A and G, that also we don't know. So C and F, B and G. C and F, C is here and F is here, we don't know about C and F. And do we know anything about B and G? For B and G, yeah, but it will come in the next iteration. So in the first iteration we have found few, but for the next iteration we have already seen that A and B could be crossed, and E, this also could be crossed because of E, and this could be crossed because of B and D. So B is here, D, because of B and D we can cross this also, and similarly this can be crossed because of A and B. A and B are not equivalent, so this particular cell can also be not equivalent. Now because of them, because of these newly found crosses, so we can cross this also. This is crossed because of B and G, which we have recently crossed. So because B and G cannot be equivalent, so because of that H and F also cannot be equivalent. So similarly for B and G, we can cross this also. This is again because of B and D. This is B and D, because of B and D this is also not, because B and D is not equivalent, because of that A and G is also not equivalent. Now because A and G is not equivalent, so this is also not equivalent. C and E, this is because of D and G. So now D and G is not equivalent, so this is also not equivalent. And because we have removed A and G are not equivalent, so this A, E and H is also not equivalent. So this we are trying to do recursively. So as soon as one particular pair says that they cannot be equivalent, because of that some other pair will also say they cannot be equivalent. So if we remove all of them, what we have seen finally is there are two pairs which are left, C and E and A and D. So if you see this pair A and D depends on C and E, and C and E pair depends on A and D. So this appears that this A is equivalent to D and C is equivalent to E. So if we do that, so let's say we replace here with C and E are equivalent, so that means A and D are equivalent. If A and D are equivalent, that means C and E are equivalent. So these two conditions crosses with each other, and we can conclude that A is equivalent to D and C is equivalent to E. So in the next step, what we should do is we should replace the original table wherever D was there, we'll replace them with A, and wherever E was there, we'll replace it with C. So when we replace them, then what do we see? We see that these two rows become redundant. So AAC 0, and we see AAC 0 here also. Similarly, we see CC, we can remove this, and now we see CCA1, and here also we see CCA1, so we can remove this also. So this would be the final. If we remove these two rows, this would be finally reduced row. So using this whole exercise, we are able to find two redundant states, and then we can say that whatever state machine will come out of that, it would be optimized one, because we have removed all the possible redundant states. Okay, so this is how we can reduce the state machines.